When we gaze out across the vastness of space, we're confronted with deep questions reflecting the core of our humanity. Where do we come from? What does the future hold? And perhaps, most profoundly, are we alone in the universe? What if I told you that an answer to this most ancient question may be just over the horizon? I'm excited to share with you a new way to search for signs of life beyond Earth. We have just published a research paper demonstrating that rocky planets orbiting white dwarfs, the smouldering cores of long dead stars, could be our best hope in the near future to find alien life. We call this the White Dwarf Opportunity. Today, we're going to dive into the extraordinary progress in exoplanet astronomy. We'll see how to peer into the atmospheres of these distant worlds. We'll examine the chemical fingerprints of life. And finally, why planets orbiting dead stars could be the key to find life in the universe. For most of human history, we only knew of the 6 planets in our solar system visible to the naked eye: Mercury, Venus, Earth, Mars, Jupiter and Saturn. But that didn't stop us from imagining worlds around other stars. In 1584, the Italian friar Giordano Bruno made an extraordinary claim that the stars we see in the nighttime sky have their own planets, including planets like Earth, but we can't see them because their stars are far brighter. This remarkable insight, published 24 years before the invention of the telescope, highlights the extreme challenges in detecting planets orbiting other stars, what we now call exoplanets. The first claimed evidence of an exoplanet was published in 1855 when the director of the Madras Observatory in India, Captain William S. Jacob, reported strange deviations in the orbits of a binary star system. This claim, and many others in the following century, were eventually shown not to be planets, but they did establish the idea that astronomy could be used to search for worlds around other stars. The first confirmed exoplanets were detected in 1992 from observations of a pulsar, a magnetized rotating neutron star, the remnant of a supernova explosion. Just 3 years later, in 1995, the first exoplanet around a Sun-like star, 51 Pegasi b, was announced. The discovery of this gas giant, orbiting 7 times closer than Mercury, kick-started the modern field of exoplanet science, as recognised by the Nobel Prize in Physics in 2019. Over the last 25 years, exoplanet discoveries have continually surprised us. We found inferno gas giants with comet-like tails, massive lava worlds with molten surfaces, and even a rocky planet in the habitable zone of our nearest star. Our galaxy appears to be teeming with worlds. On average, every star hosts at least one planet, and around 1 in 4 stars is likely to host an Earth-sized planet in its habitable zone. So far, over 4,000 exoplanets have been discovered, with more reported on an almost daily basis. Remarkably, the vast majority of these discoveries were found without even directly seeing the planet. Most exoplanet detections in the 90s and 2000s came from observations of how the light from a star changes as one or more orbiting planets gravitationally tug on its parent star. When the star moves away from our line of sight, its light becomes slightly redder, and when it moves towards us, the light becomes bluer, with the size of the shift helping us constrain the mass of the planet. We call this the radial velocity method. But the greatest surge in known exoplanets has come from a different but complementary direction. In 2009, NASA's Kepler Space Telescope was launched. Kepler's mission was to stare at hundreds of thousands of stars, watching for periodic dips in the amount of light they emit, a telltale sign of an exoplanet passing in front of the star it orbits. Crucially, the fraction of starlight blocked by the planet allows us to measure the planet's size. We call this the transit method. Kepler was an extraordinary success, leading to over 2,800 confirmed planets and achieving its goal of finding many Earth-sized exoplanets lying in the habitable zone. Though now retired, Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS, was launched in 2018 to continue the search. TESS is currently surveying the sky looking for transiting planets around nearby bright stars. To date, TESS has found over 67 confirmed planets and over 2,000 candidate objects awaiting confirmation. The exciting thing about these planets is that they are much closer to Earth than the planets discovered by Kepler, and are therefore great targets for atmospheric characterization. So how do we measure what the atmospheres of planets hundreds of light years away are made of? There are a number of ways to do this, but the most successful technique is called transmission spectroscopy. The key idea is to observe an exoplanet transit in different wavelengths or colours of light. At wavelengths where molecules or atoms in the planet's atmosphere strongly absorb light, the planet will appear slightly larger, while at wavelengths where the atmosphere is more transparent, the planet appears smaller. By measuring how the planet's size varies with wavelength, often from visible light to the infrared, we construct what we call a transmission spectrum. And because every molecule in the atmosphere interacts with light in a distinct way, leaving a unique chemical fingerprint in the planet's transmission spectrum, we can reverse engineer these observations to figure out what the atmosphere is made of. Since the first exoplanet atmosphere was observed in 2002, we've studied around 50 planets using this method, yielding some quite incredible results. We've found planets with ionized metals floating in their dayside skies, planets shrouded in mineral clouds where it rains rubies and sapphires, and we've detected water vapour in over a dozen planets. In many ways, it appears the universe is far stranger than imagined by science fiction. Most of the planets we've characterised to date are giant planets with temperatures higher than 1000 degrees Celsius. We call these objects hot Jupiters. We do also have a few atmospheric detections from planets around the mass of Neptune, but this is about the limit of currently operating telescopes. In particular, NASA's Hubble Space Telescope and the recently retired Spitzer Space Telescope have been fundamental to many of these discoveries, and I'd like to highlight that much of this wouldn't have been possible without the 2009 Space Shuttle servicing mission to Hubble, which installed a new infrared camera that has proven fundamental to detecting molecules in exoplanet atmospheres. Alongside Hubble and Spitzer, many large telescopes on the ground, such as the Very Large Telescope Array in Chile, have made important discoveries about exoplanet atmospheres. So everything I've spoken about so far is for giant planet atmospheres. What about rocky planets? To see why terrestrial planet atmospheres are harder to characterise, let's compare a typical hot Jupiter to an Earth-like planet. To first order, the amount of light absorbed by a planet's atmosphere during transit is proportional to the height of the atmosphere. This is roughly given by the expression seen here, where T is the temperature of the planet, G is the gravitational acceleration, the Greek letter mu is the average mass of the molecules making up the atmosphere, and K is the Boltzmann constant. So if we plug in representative numbers for Earth, we find a height of around 85 kilometers. But for a typical hot Jupiter, the height comes out much larger, around 5,000 kilometers. So the atmospheres of Earth-like exoplanets are roughly 60 times smaller than the giant planets we routinely characterise today, resulting in much weaker absorption signatures. The two reasons for this are the lower temperatures of planets in the habitable zone, and that molecules like nitrogen and oxygen, which dominate Earth's atmosphere, are far heavier than the hydrogen and helium that gas giants are made of. So while this puts Earth-like atmospheres a little beyond what we can currently analyse with telescopes like Hubble, we will be able to characterise them very soon with upcoming telescopes. Our first opportunity to study the atmospheres of potentially Earth-like exoplanets will come with the launch of NASA's James Webb Space Telescope next year. James Webb has a 6 times greater collecting area than Hubble, boasting a 6.5 metre primary mirror. It features a suite of visible and infrared detectors covering a much larger wavelength range than Hubble, while also being more sensitive and capable of higher resolution observations. Another advantage is that James Webb will reside beyond the Moon, orbiting at the L2 Lagrange point, enabling continual observations, which is an issue for Hubble as it orbits Earth every 96 minutes. James Webb is now fully assembled and undergoing tests to verify the hardware and software is ready for launch. It is planned to ship to French Guiana next summer and launch on a European Ariane 5 rocket in October 2021. The telescope will then deploy over a 2-week period on its way to L2, with the first science observations commencing 6 months after launch. So from early 2022, our first observatory capable of looking for life in the cosmos will be ready to begin the search. In 1990, the Galileo spacecraft flew by Earth on its way to Jupiter. During its flyby, legendary astronomer Carl Sagan used Galileo to conduct one of the most important experiments in astrobiology. In a landmark 1993 paper, Sagan and collaborators showed that Galileo data alone was sufficient to infer the existence of life on Earth. 2 pieces of evidence were particularly compelling. The first was the existence of large quantities of gases, namely oxygen and methane, which should be rapidly destroyed by standard atmospheric chemistry, requiring a large continual source to replenish them, when the only plausible explanation of such an anomaly is biological processes. This is called a biosignature. The second strong piece of evidence for life on Earth was amplitude-modulated radio transmissions, an unambiguous sign of a technological civilization. Radio transmissions such as these are one example of what we call a technosignature. The Galileo flyby of Earth 30 years ago remains to this day an important control experiment for how to detect signs of life via remote observations. Indeed, many of its findings carry over to the modern search for life on exoplanets. When we think about searching for life on exoplanets, a good first step is to consider which molecules are produced by life on Earth. Let's start with the 2 molecules that constitute some of the strongest evidence for life on Earth: oxygen and methane. The oxygen we breathe, making up 21% of Earth's atmosphere, is largely produced by photosynthesis from plants. Our methane, meanwhile, comes mainly from 2 processes. 1/3 comes from microorganisms undergoing anaerobic respiration, while the other 2/3 comes from human industry and agriculture. Another gas often discussed is ozone, which is produced by ultraviolet light interacting with oxygen in Earth's upper atmosphere. Ozone turns out to be far easier to detect than oxygen, even though it's 10 million times less abundant on Earth. So it's a useful proxy for oxygen, even though ozone isn't directly produced by life. 2 further gases we could look for are nitrogen and nitrous oxide, both of which are produced by bacteria in soils and sediments as part of Earth's nitrogen cycle. Similarly to oxygen, molecular nitrogen has very weak absorption features, so will be quite difficult to detect on exoplanets. But nitrous oxide, more widely known as laughing gas, has relatively strong absorption features. Finally, I want to highlight one molecule which has attracted attention in recent years as a potential biosignature: phosphine. Trace quantities of phosphine are produced in anaerobic ecosystems and are also released by some industrial activities. There are, of course, other gases besides these produced by life, such as some sulfur-bearing molecules, but these gases have such low abundances on Earth that they usually aren't considered good candidates to be detectable in exoplanet spectra. Now imagine that you've detected some of these gases in an exoplanet atmosphere. To assess whether or not this constitutes evidence for life, you have to also consider non-biological ways to make each molecule. For example, a false positive for oxygen would be a planet with an evaporating ocean due to a runaway greenhouse effect, similar to what happened on the early Venus. The water vapour in such a scenario can be split into hydrogen and oxygen by ultraviolet radiation, with the light hydrogen molecules escaping the atmosphere and leaving behind plentiful oxygen entirely without the need for life. Similarly, methane can be produced by volcanoes or geological activity, and nitrogen can be accreted during planetary formation or delivered by comets. But nitrous oxide and phosphine have very few non-biological production mechanisms, with, for example, only minor amounts of nitrous oxide produced by lightning strikes. When we think about biosignatures, the key insight is not to look for individual molecules, but to look for combinations of them that strongly imply the presence of life. For example, the combination of oxygen and methane is thought to be a good biosignature because these two molecules react together very quickly. In fact, it would only take around 10 years for the methane in Earth's atmosphere to react away if it wasn't for life continually replenishing it. We call this a disequilibrium biosignature. A similar argument identifies the combination of oxygen and nitrous oxide as a biosignature, with a lifetime of around 100 years without biological production of nitrous oxide. A disequilibrium biosignature does not just have to include gases though, as the combination of nitrogen, oxygen and liquid water in Earth's oceans would react to form nitric acid were it not for biological processes. So here are 3 potential biosignatures we can look for on exoplanets. But since oxygen and nitrogen have very weak absorption features, in practice ozone is far more detectable, and so ozone plus methane or ozone plus nitrous oxide are considered some of the best biosignatures to search for in exoplanet spectra. Of course, this is specific to life as we know it on Earth, but the general idea of looking for combinations of gases that are far out of equilibrium should still allow the inference of potentially very different alien biochemistries. Okay, so now we know what biosignatures to look for. Where should we search to try to find alien life? Imagine for a moment that you are a distant observer watching Earth transit the Sun. The Earth is 109 times smaller than the Sun, so it only blocks out about 0.01% of the Sun's surface during transit. But if the Earth was orbiting a smaller star, the fraction of the star's surface covered by the planet and its atmosphere will be greater, producing more detectable absorption features. In particular, a type of star we call M-dwarfs, also known as red dwarfs, can be around 10 times smaller than the Sun, so an Earth-sized planet orbiting an M-dwarf can block out around 1% of its star's light during transit. Another advantage of looking for such planets is that the M-stars are much cooler than the Sun, so the habitable zone can be around 50 times closer than Earth's orbit. So instead of waiting 365 days for a transit, a habitable planet around an M-dwarf transits about once a week. Taken together, the enhanced atmospheric detectability and frequent transits for rocky planets around small stars like M-dwarfs has been termed the small star opportunity. Perhaps the most well-known example of planets around an M-dwarf is the TRAPPIST-1 system. First discovered in 2016, TRAPPIST-1 is a star 40 light-years away, orbited by 7 terrestrial planets, 3 of which lie in the star's habitable zone. Transmission spectral observations with Hubble have already been reported for the 6 innermost planets, ruling out hydrogen-dominated atmospheres. We don't currently know whether or not the planets have atmospheres similar to Earth, or Venus, or perhaps something entirely different. But some of the first observations with the James Webb Space Telescope will be targeting the TRAPPIST-1 planets to provide some answers. Based on theoretical modelling, we believe the planet most likely to have conditions similar to Earth is the 4th planet in the system, TRAPPIST-1e. If this planet does indeed have an Earth-like atmosphere, it should be possible to detect carbon dioxide within around 10 transit observations with James Webb. Detecting biosignatures, such as ozone plus methane, is also possible, but will require more observation time. Models suggest that at least 100 transits of TRAPPIST-1e would be required to detect Earth-like biosignatures with James Webb. Given that this planet transits once every 6 days, and TRAPPIST-1's location in the sky is visible to James Webb for about 100 days per year, observing these 100 transits would take around 6 years. So I imagine you might be wondering now whether there could be a faster way to search for biosignatures in exoplanet atmospheres. Well, we have just published a paper that might just have a solution to accelerating our search for life in the universe. One day in the future, every star will come to an end. The most massive stars end their lives in violent supernova explosions, briefly shining brighter than an entire galaxy. But over 95% of stars, including our own Sun, are not massive enough to go supernova. Around 5 billion years from now, the Sun's core will exhaust the hydrogen fuel powering nuclear fusion into helium. It will then evolve into a red giant star powered by helium fusion, causing it to dramatically expand to as far out as Earth's orbit. But even the red giant phase won't last, as over the course of 1 billion years or so, the Sun will build up an inert core of carbon and oxygen which can no longer fuse. Without the outwards force caused by nuclear fusion, gravity will cause the Sun to collapse inwards, with its outer layers expelled into space, leaving behind its exposed core, the last remnant of a dead star, a white dwarf. White dwarfs are remarkably small and dense objects. They can have a mass similar to the Sun, but a size only a little larger than the Earth. The only thing stopping white dwarfs from collapsing down even further to a neutron star or a black hole is a quantum phenomenon called electron degeneracy pressure. Imagine for a moment a planet the size of Earth orbiting a white dwarf. During transit, around half of the light from the white dwarf would be blocked. Do planets like this actually exist? Well, one of the strange things about white dwarfs is that at least a quarter of them have signatures of heavy elements such as iron, nickel and titanium in their spectra. These elements aren't produced during the evolution of the star that became the white dwarf, and they should sink out of view on timescales ranging from days to millions of years. So there must be an external source contaminating many white dwarfs. We now believe the source of this contamination is rocky objects, such as asteroids and minor planets, being ripped apart by the high-gravity tidal forces near to white dwarfs, continually supplying them with heavy elements. So we have indirect evidence of rocky bodies in white dwarf systems, and in fact the first evidence goes as far back as 1917, but it wasn't recognised as such until much later. But until now, there hasn't been any evidence that an intact planet can survive around a white dwarf. On September 16th, 2020, NASA announced the discovery of the first transiting planet orbiting a white dwarf. Known as WD-1856b, this giant planet, 80 light-years away, is around 90% the size of Jupiter, making it 7 times larger than its white dwarf host, and orbits in just 34 hours. First observed by NASA's TESS mission in July last year, the planet has since been observed by multiple ground-based telescopes and the Spitzer Space Telescope. A planet orbiting this close would have been incinerated during the red giant phase, so it must have originally come from further in the system before being perturbed somehow to its current orbit. When I first heard about the discovery of WD-1856b earlier this year, my mind was racing with exciting possibilities. In particular, I started discussing the prospects of rocky planets around white dwarfs with my colleagues, Professor Lisa Kaltnager and Dr. Thea Kazakis at the Carl Sagan Institute in Cornell University. Because we now know that a giant planet can survive around a white dwarf, it's actually quite plausible that intact rocky planets could survive around white dwarfs. So our idea was to calculate how easy it would be to detect biosignatures in the atmospheres of Earth-like exoplanets transiting white dwarfs with the James Webb Space Telescope. And what we found was quite remarkable. An Earth-like planet around a white dwarf would have started its life in the outer star system before migrating or being scattered inwards after the red giant phase. White dwarfs gradually cool over their lifetime, starting at many tens of thousands of degrees, but after about 2 billion years, they reach temperatures around 6,000 Kelvin, where close-in planets can support liquid water for twice as long as the Earth will be habitable. The white dwarf habitable zone is around 100 times closer in than the Earth orbits the Sun, meaning that the planet's year would last just 10 hours, so an Earth-sized planet transiting a white dwarf would block out around half its light during a 2-minute transit event, with 2 transits taking place every day. The really exciting thing is that the atmospheric signals of such a planet would be incredibly strong because of the large area of the white dwarf surface covered by the planet's atmosphere, so it would be much quicker to collect high-quality atmospheric data for planets transiting white dwarfs. In our new paper, The White Dwarf Opportunity, which has just been published in the Astrophysical Journal Letters, we detail the prospects for detecting molecules in Earth-like atmospheres transiting white dwarfs. We created an atmospheric model of what an imagined Earth-like planet evolving in the habitable zone of a white dwarf like WD-1856 would be made of. The same molecules we see in Earth's atmosphere, such as oxygen, nitrogen, methane and ozone, are all there, but we calculated how the different amount of ultraviolet radiation received by the planet would change its atmospheric composition. We then computed what the planet's transmission spectrum would look like, noting where each molecule has strong absorption features, and simulated James Webb observations of our notional planet. Our goal was to see how many transits would have to be combined to make the error bars small enough to conclusively detect each molecule and biosignature pair in the atmosphere. This was done using the atmospheric retrieval code Poseidon, which I developed during my PhD, which you can find more about in the video up there and down in the description. Our calculations showed that James Webb will be able to rapidly measure the composition of Earth-like exoplanets transiting white dwarfs. This diagram from our paper shows how many transits are required to conclusively detect each molecule. Only 5 transits, or about 10 hours of James Webb observing time, would result in secure detections of water and carbon dioxide. But what we're really excited about is that just 25 transits, a little over 2 days of James Webb observations, would secure a detection of the ozone plus methane biosignature. And given that each transit occurs every 10 hours, it would only take a 2-week observing campaign to detect this biosignature for a habitable planet with life around a white dwarf. If you're willing to observe for a few more weeks, you can also detect the ozone plus nitrous oxide biosignature, and even nitrogen plus oxygen, despite their weak absorption features. So if rocky planets do indeed exist around white dwarfs, we have shown that they could be the best targets to rapidly search for signs of life beyond the solar system. But to realise the white dwarf opportunity, we need to find transiting planets around white dwarfs. As we speak, NASA's TESS mission is undertaking a survey hunting for transiting planets around white dwarfs. Since these events should block out around half the light from a white dwarf and occur multiple times per day, ground-based telescopes should also be capable of easily seeing them and helping the search. Our calculations suggest that any white dwarf within 200 light-years hosting an Earth-like planet would be a fantastic target for transmission spectroscopy. And in fact, the European Space Agency's Gaia mission tells us that there are almost 5,000 white dwarfs within 200 light-years of Earth. So while we haven't found a rocky planet around a white dwarf just yet, there are thousands of these dead stars nearby just waiting to be searched. And imagine what it would mean if we succeeded. If we found signs of life on a planet orbiting a dead star, we would know that the death of a star is not the end of the story for life, that life can survive, thrive, and flourish even into the distant future of our universe. The answer to our most ancient question could lie in the most unexpected place, on a world illuminated by the remnant core of a long-forgotten star. If you enjoyed this video, be sure to check out my other content on planetary science and human missions to Mars. To make sure you don't miss future videos, hit subscribe, click the notification bell, and I'll see you next time.